Hello everyone. In this lecture we will take the discussion forward from the previous lecture and have a look at some of the applications of the Gauss law. So to remind you of what the Gauss law is, in the last lecture we saw that the Gauss law says that the flux of the electric field E through any closed surface, which is basically the surface integral of the electric field, it equals 1 by epsilon naught times the total charge which is enclosed by the surface. So the total charge enclosed, we could find it in any way, and because it's just it is independent of the actual nature of the charge. All that matters is the total charge. So we can find out this Q enclosed either as a summation in case it's a discrete distribution, or we could find it as an integral in case it's a continuous distribution of charge. So now we will see how symmetry plays a role in applying the Gauss law when it comes to finding the electric field in certain kind of distributions. So now when we say symmetry, what comes to our mind is immediately objects like, for example, this butterfly. We immediately have an instinct that this butterfly is symmetric, but then we need some kind of qualitative markers which will help us to judge the kind of symmetry that we are seeing. So we define certain things. So for instance, we define something called as an axis of symmetry. So what is the axis of symmetry? It is any line that divides the figure into two symmetrical parts such that the part of the object on one side is the mirror image on the other side. As you can see here, this red line, it represents it is the axis of symmetry in the case of this butterfly. So whatever you see on the right side of this red line, it's the mirror image of whatever you see on the left side. Then you could another feature of the axis of symmetry is that you could rotate this object about this axis of symmetry by a certain fixed angle, and the pattern is going to repeat itself. So in this case, in the case of the butterfly, you could rotate it by 360 degrees and it is the pattern is going to keep on repeating. Then we could also talk about what is the line of symmetry. Now the line of symmetry could have many different definitions. Now for the sake of simplifying the problems that we're trying to solve, I define the line of symmetry this way. Okay, so the line of symmetry is the line which is perpendicular to the axis of symmetry and passing through the center of the object. So let's say I find the center of the butterfly to be over here. Then the line of symmetry is a line which is perpendicular to the axis of symmetry. And another thing to note here is the axis of symmetry, this is also a line of symmetry. So if I go a certain distance along the line of symmetry and I go the same distance on the in the other direction, I will reach the exact same point. So this point and this point, these points are exactly identical, okay, with respect to the symmetry of this figure. So these are two things that we will define here, axis of symmetry and the line of symmetry, and we will apply these ideas to the symmetric charge distributions that we are going to consider, and see how we can use we can exploit those symmetry symmetry of the distribution and use the Gauss law to simplify the problem. So let us see how we can use that. This approach that we are going to follow, it is applicable to the following types of symmetry. First is the spherical symmetry, then we have cylindrical symmetry, and finally we have planar symmetry. So what we see over here is a spherical symmetry. So how do you characterize spherical symmetry? We can characterize spherical symmetry by the ability to have an infinite number of symmetry axes which pass through the same point. So here you see there is a certain point which we denote as the center of the distribution. Then if we can pass infinite number of such axes of symmetry through this point, then that's a spherical symmetry. That means any of these axes could be an axis of symmetry. That means you could rotate this about any of these axes. So I could rotate this about this axis, I could rotate this about this axis or this axis. The distribution is going to remain the same. In case of a charge distribution with a spherical symmetry, there are certain things that we need to keep in mind. The electric field vector will be along any line of symmetry. So for instance, let's say I take this axis of symmetry. So the line of symmetry will be perpendicular to this. That's how we have defined this. And we see that the line of symmetry itself is an axis of symmetry. Okay, so we can say that the electric field vector is along any line of symmetry or along any axis of symmetry. So the electric field is always going to be along the axis of symmetry or the line of symmetry in case of a spherical of a charge distribution with a spherical symmetry. Okay, and this direction is also what is known as the radial direction. And the second thing is, like we saw in the case of the butterfly, if you move the same distance, okay, on either side along a line of symmetry, the situation looks exactly the same. So in a similar way, if I move a certain distance, let's say some distance a along this direction, and I move the same distance a along this direction, then the distribution here and the distribution here will be exactly identical, and so the electric field at this point and the electric field at this point will also be identical. Okay, so the electric field has got the same magnitude at all points which are equidistant from the center. So these are the 2 points that we need to keep in mind when we are talking about a spherical symmetry. So let us consider a Gaussian surface which looks like this. So this is a Gaussian surface. Now if you remember, Gaussian surface is an arbitrary imaginary surface. So you have to imagine the Gaussian surface. It does not really exist. You have to imagine it for the sake of finding the surface integral of the electric field or for finding the electric flux. So we have to imagine a Gaussian surface. So in case of spherical symmetry, we choose a Gaussian surface which is spherical. Okay, so this spherical surface is the best surface which is going to help us use the spherical symmetry and help us find out the electric field. We might have chosen let's say a surface which is like a, let's say, cube. That also would have given us the flux, but that would not give us the field. Okay, because if you remember, flux is the surface integral of the electric field. So choosing any other surface, that would have given us only the flux. But if you want to know the field, if you want to extract the field from that surface integral, then we need to choose a surface which is spherical. Okay, so this is our Gaussian surface. Now keeping in mind these 2 points, at every point on the Gaussian surface, the electric field will have the same magnitude, simply because at every point the distance from the center is the same, which is r, and we know that it has got at the same magnitude at all points which are equidistant from the center. Okay, so the electric field has got the same magnitude everywhere. Secondly, the electric field is along the radial direction. So electric field is along the radial direction. Now we also know that the surface, if I have a small surface vector, area vector at this point, that area vector also is going to be radial, because for a sphere, okay, the normal to the sphere is going to be perpendicular to the surface, and the normal is also going to be along the radial direction. So electric field is also along the radial direction, the area vector is also along the radial direction. So E and dA, they are parallel to each other in case it's a positive charge. In case it's a negative charge, and E and dr will be anti-parallel. But the fact remains is that E and dA, they are going to be along the same line. So E dot dA is equal to E dA. Okay, so at each and every point on this surface, E dot dA is equal to E dA, where E is a constant. So the total flux in this case will simply be, E times the area of the sphere. How do we get this? So when we integrate this, I told you that the electric field has got the same magnitude. So E is same everywhere on the surface over which we are integrating. So E is going to come outside. So we are integrating the surface of a sphere. So that means E you have to multiply. This is the result of the integral, which is the area of the sphere. So E you have to multiply with the area of the sphere, and area of the Gaussian surface, which is a sphere, is, we know very well, it is 4 pi r square. So the total electric flux through this Gaussian surface is going to be equal to 4 pi r square into E. Then according to the Gauss law, we have the flux must be equal to 1 by epsilon naught times the charge which is enclosed. So the flux, which is 4 pi r square E, it must be equal to 1 by epsilon naught times the charge which is enclosed inside this Gaussian surface. So that's about distributions which have a spherical symmetry. Then we come to cylindrical symmetry. So a cylindrical symmetry, how do we characterize it? We can characterize it by the existence of a unique axis of symmetry. So it has got a single axis of symmetry. Okay, there is a unique axis of symmetry. That axis of symmetry is it characterizes the spherical symmetry, a distribution with a spherical symmetry. So let's say if I have a line, a single line, okay, which is I have charge which is distributed over a single line, that becomes a cylindrical symmetry. Then in the case of cylindrical symmetry, because there is a unique line of axis, so any point on this line of axis may be considered to be the center of the distribution. So there is no unique center. The axis of symmetry is unique, but the center of the distribution is not unique. So in case of a charge distribution with a cylindrical symmetry, so these are our 2 points about the electric field. The electric field is along any line of symmetry. So again, like I said, any point can be at the center, and the line of symmetry, we define it as a line which is perpendicular to the axis of symmetry and passing through the center. So any point can be the center. So let's say I take a center over here, then the line of symmetry will be a direction which is perpendicular, which is in this direction. Okay, the electric field is along any line of symmetry. So due to this distribution, if I take any point, you take the line of symmetry, the electric field will be in this direction, and if you go over here, well, the electric field at this point will be in this direction, okay, and so on. So it will be radiating outward from this particular line, okay. So that will be the direction of the electric field vector, and the electric field has the same magnitude at all points which are equidistant from the symmetry axis. So if I have a point, let's say from here at this point at certain distance a, another point which is at the same distance a, the electric field at this point and the electric field at this point will be the same. So to understand that, we can imagine a Gaussian surface, and this Gaussian surface also is going to be cylindrical. So we have this Gaussian surface whose radius is which is a cylinder, and the radius of the cross sectional area is the cross section is going to be a circle, and the radius of the circle is r, and this cylinder has got a length L, okay. So if you apply these 2 points, the electric field vector, okay, let's say on this surface, this curved surface, the electric field at this point, this curved surface, will be always perpendicular to the surface, that is in the radial direction, and the electric field will be same at all points on the surface. The second point, it says that the electric field will be same at all points on this curved surface. But the cylinder has got 2 flat surfaces also, that is this surface and this surface. So this flat surface, if you look at it at this point, the normal vector will be in this way, right? The normal vector is always perpendicular to the surface, so the normal vector will be pointing this way, but whereas the electric field here also will be in the radial direction. So now on the flat surface, what happens is that the normal direction and the electric field, they are perpendicular to each other, and if they are perpendicular, we know that the flux is going to be 0, because flux is basically the dot product of the area vector and the electric field. So E dot A into cos of 90, which is going to give us 0. So this surface is not going to contribute to the flux, as also this back end surface. These 2 flat surfaces, they do not contribute to the total flux. So the total flux will be contributed only due to this curved surface. So we can find out that the total flux, it becomes equal to the electric field times the area of this curved surface. And what is the area of the curved surface? It is simply the circumference of the circle times the length of the cylinder. So 2 pi r, which is the circumference of the circle, times the length of the cylinder. So 2 pi r LE. Okay. So now just applying the Gauss law, we have the 2 pi r LE, this is the total flux. It must be equal to 1 by epsilon naught times whatever is the total charge that is enclosed inside this cylinder. So that's about cylindrical symmetry. Now coming to planar symmetry. So we can characterize planar symmetry by the existence of an infinite number of axes of symmetry, all of which lie on a plane. So we have a single plane, and on this plane we could have an infinite number of axes of symmetry. So this could be an axis of symmetry, this could be an axis of symmetry, this could be an axis of symmetry, okay. Any line which lies on this plane could be an axis of symmetry. So let us say in case of this charge distribution with a planar symmetry, the electric field vector is along any line of symmetry, okay. So again, because any of these axes could be an axis of symmetry, I could choose any point as the center. So the line of symmetry, so let's say I choose this line as the axis of symmetry, and I choose this point, let's say, as the center, then the line of symmetry will be perpendicular, so it will be pointing, it will be piercing into the plane. So all lines of symmetry will pierce into the plane. The electric field will be along these lines which pierce into this particular plane, okay. So that will be radiating perpendicular to the plane of the distribution. And secondly, once again the same thing, the electric field will be having the same magnitude at all points which are equidistant from the plane, okay. So what kind of a Gaussian surface we can choose? Here I have chosen what is called as a pillbox surface. So pillbox surface basically looks like this, okay, like a rectangular box, okay, which straddles this surface with equal amounts of this box on this side and on the other side. So basically you consider a rectangular box such that the plane intersects the box and it cuts into two equal halves, and the area of cross section of this box is A. Okay, so here even though I have shown it to be like a rectangular box, but you might as well choose it to be a cylindrical box also, as we will see in the example that we do. But actually speaking, you don't even require a regular shape like box. You could have any box of any cross sectional area, so long as the cross sectional area remains the same, okay, along the length of the box, that is going to work. Okay, so now if you look at this box here, the box has got a front surface and a back surface, but here the side surface of the box, they don't contribute to the flux. You can see how, because on the side surface the area vector is going to be pointing in this way, but the electric field is going to be radially outwards. So once again the normal vector and the electric field, they will be perpendicular to each other. So the flux due to the side surface, that is going to be 0. So the side surfaces, they do not contribute to the total flux. So as a result, the total flux is going to become equal to electric field times the total area. The total area of the front face and the area total area means the area of the front face plus the area of the back face. Area of either of the faces is A, so the total area is going to be equal to twice A. So the electric field times the total area, which is twice A, that is going to be the total flux. Then according to the Gauss law, we have total flux, which is twice AE, which is equal to 1 by epsilon naught times the charge which is enclosed inside this pillbox surface. Okay, so what I have given over here are these general expressions we can use. So in case of a distribution with let's say spherical symmetry, so suppose I have a distribution with spherical symmetry, we can just pick up this expression, okay, this expression of the Gauss law, and just apply it. Wherever there is spherical symmetry, we can just pick this up and apply it. In case we have a cylindrical symmetry, then we can just pick up this final expression here and we can work with this. And in case we have a planar symmetry, we can just pick up this last expression of the Gauss law and we can work with this. Okay, so let's now apply this to the case of a spherical charge distribution. So here we consider a charge which is distributed uniformly, okay, over a sphere of radius r. So we have a sphere which is having a radius capital R, and the charge, a total charge, let's say capital Q, is distributed over this entire sphere, and this is distributed with a uniform density of rho. Okay, so a spherical charge distribution, just to be clear, because it may not be uniform. Okay, there may be a scenario where it may be non-uniform also. So how do you define a spherical charge distribution? We define a spherical charge distribution as one in which the charge density depends only on the radial distance from a central point. So only from the central point, the charge distribution, charge density depends only on the distance from a central point. So now over here we have a uniform density, so rho is going to be constant in this case. Okay, that's what you need to remember. So we want to find out the electric fields inside the sphere as well as outside. So now remember, the charge is distributed over the entire volume. So we have charge inside this sphere also, and we have charge on the surface also. Okay, so we need to find out the electric field inside as well as outside. Okay, inside this volume as well as outside this volume. Okay, that's why we need to find out the electric field. So what we'll do is, again, if you remember, some time back we saw for a distribution with spherical symmetry, the Gaussian surface is also a spherical surface which is concentric with the distribution itself. Okay, so we have a Gaussian surface which is also spherical and concentric with the distribution, and let's say that this Gaussian surface has got a radius r. Then we have to consider two different Gaussian surfaces, because we want to find out the field inside as well as outside. So we need to consider two scenarios. Okay, so this is the distribution, this is the original distribution. So if I take, this is the Gaussian surface, okay, this is the original distribution, and this is the Gaussian surface that we imagine here. So this Gaussian surface has got a radius of small r. For points outside, for points which lie outside, now remember the Gaussian surface should include that point, okay, should include that point on its surface. So if I consider the point which are lying outside, then the Gaussian surface should include that point, which means the radius of the Gaussian surface, it must be greater than or equal to the radius of the sphere itself. So this is for the points outside, and for points inside, the Gaussian surface will be completely inside the sphere. So the radius of this Gaussian surface will be lesser than the radius of the sphere. Okay, so if you want to find field inside as outside, we just need to consider these two cases: r greater than capital R greater than equal to capital R, or R less than capital R. So these are the two cases which will take here. Okay, so now let's see what happens at the fields due to at the exterior points. Okay, so that is R greater than or equal to capital R. So exterior points, we want to find out the field. So total flux for the Gaussian surface, we already know it is 4 pi r square E. This 4 pi r square comes from the spherical symmetry, and E is a constant, so it comes outside the integral. So that's why we have 4 pi r square E, as we saw some time back. And the total flux will simply be Q enclosed. Okay, so what is the total the total charge? The total charge through this inside, which is enclosed inside this Gaussian surface. The total charge is nothing but the total charge which is contained inside this spherical volume of radius r. So all you need to do is this rho, which is the volume charge density. You just have to multiply it with the volume of this charge distribution, and the volume of this charge distribution is 4 by 3 pi r cube. So rho into 4 by 3 pi r cube, that is going to be the charge which is enclosed inside the Gaussian surface. And we know that according to the Gauss law, this flux must be equal to 1 by epsilon naught times this charge enclosed. Okay, so now of course let's say the total charge over here, let's say we call it as capital Q. Okay, then by Gauss law we have 4 pi r square E is equal to 1 by epsilon naught times this, which is 4 by r square rho r to the r cube, capital R cube. So when you simplify this, you see that this 4 pi will get cancelled out. Okay, and what will be left behind is rho into r cube, and this r square goes down, and there is already the 3 here. So we have the electric field at any point on the Gaussian surface. That means at all points which are outside the which are outside this distribution, the electric field will have a magnitude which is equal to rho r cube by 3 epsilon naught r square. Okay, now instead of rho, if the total charge is given, okay, then this is going to be simply Q, so Q by epsilon naught, and then 4 by r square comes on this side. So this will give us the electric field to be 1 by 4 pi epsilon naught Q by r square. But the moment I look at this expression, what is this? This is K Q by r square, which is basically the electric field due to a point charge, right? So this suggests that for points which are outside the spherical distribution, the entire charge, because it's like as if this is a point charge, it's like as if the total charge, which is Q, it seems to be distributed at the center of the sphere. Okay, the entire charge seems to be concentrated at the center of the sphere. So this actually kind of reminds us of the concept of the center of mass. So like the center of mass, it seems like as if where the entire mass seems to be distributed to be concentrated at that point, which we call as the center of mass. Here the total charge seems to be concentrated at a single point, which we call as you could call as the center of charge. Okay, so from points outside, if I take away this distribution, this entire charge distribution, I remove this, and I place a point charge which is having the same value as the total charge inside this distribution, the effect will be same. The electric field will not be any different. It will be just the same as before. Okay, and the second thing that we realize here is the electric field is inversely proportional to r square. So electric field here, in case of for points outside, the electric field, it follows a 1 by r square relation. Then for points which are the interior, so here I consider a Gaussian surface whose radius is less than the radius of the sphere. So the total flux for this Gaussian surface, as same as before, 4 pi r square into E. I want to find out the total charge which is enclosed by the Gaussian surface. So here this is not the total charge in this sphere, it will be the total charge which is enclosed inside this Gaussian surface, that is the total charge within this region. Okay, so how do you find that? Again the same way, because this is uniform density and this is a sphere, so all we need to do is this density you have to multiply with this small sphere. So rho times 4 by 3 pi r cube. Okay, so rho times 4 by 3 pi small r cube. In the previous case, this was there was a capital R here, here it is going to be a small r. Okay, so let's say this charge which is enclosed inside, we call it as Q prime. Okay, so by Gauss law we have this must be equal to 1 by epsilon naught times this. So 1 by epsilon naught times 4 by 3 pi rho into small r cube. So over here we can see this 4 pi gets cancelled, then this r square gets cancelled, and this r square power, okay, r square from here is also going to get cancelled. So the power of r is going to become 1, okay, and this gives us rho times r divided by this nothing else is left here, okay, 3 epsilon, this is what is left. So rho times r divided by 3 epsilon naught, so that's what is left. So now instead of in terms of the charge, the part of the charge which is enclosed inside this, okay, so this is equal to q prime by epsilon naught. So this again gives us 4 pi r square, it goes on this side, so 1 by 4 pi epsilon naught q prime by r square. So that means for points which are inside, let's say points over this, I might as well take this entire charge, the charge which is enclosed inside this Gaussian surface, remove the charge and take a point charge which is equivalent, okay, which is having the same value as the charge inside this, and put it at the center. Okay, it makes no difference because this is basically the electric field due to a point charge. Okay, so this suggests that the interior points, only the charge within the Gaussian surface seems to be concentrated at the center of the sphere. And the electric field, we can see here, the electric field, it is not proportional to 1 by r square, it is proportional to r. See, it is directly proportional to r. So E is proportional to r. Okay, so that's what we observe here. Don't go by this one, because this expression, it seems like as if E is proportional to 1 by r square, but then you have to also see that there is a q prime. And what is q prime? Q prime is rho times the volume, and volume goes as r cube. So q prime is proportional to r cube. So r cube by r square, that is also going to give us a this linear variation of electric field with r. So again, that is going to give us a r. So E is always going to be proportional to r inside, for points which are inside this spherical distribution. So we could express it like this: the electric field due to this spherical distribution is going to be, for points which are inside, it is rho r by 3 epsilon naught, and for points which are outside, it is rho r cube by 3 epsilon naught r square. Okay, and the direction will be along the radial direction. And we could see the correlation here. I have just plotted the magnitude of the electric field as a function of r, and you can see here, as you go from the center to the surface, the electric field, it increases linearly. At the center of the distribution, the electric field will be 0. The electric field will be maximum at the surface, which is rho capital R by 3 epsilon naught, and you will get the same value whether you put small r equal to capital R here. So you put capital R here, so rho capital R by 3 epsilon naught, so it is this. But if I put capital R over here, so capital R cube by capital R square, so that is again going to give us a capital R by 3 epsilon naught. So you will get this. So this is not discontinuous, this function is going to be perfectly continuous here. And then once you reach the surface and from there you go outside, the electric field, it varies as 1 by r square. So this is going to be the distribution. This is how the plot of the electric field due to this distribution, this is how it's going to look like. So that's about electric field due to a spherical charge distribution. So this is one problem. I'll leave it to you to try it for yourself. You need to find out the electric field inside as well as outside a hollow sphere. So instead of a solid sphere, we consider a hollow sphere. And this hollow sphere, let's say it contains a uniform charge density of sigma. So instead of the charge being distributed over the entire volume, we have a shell. The charge is distributed on the surface of this shell, and the surface charge density is sigma. Okay, you need to find out the electric field inside as well as outside. So follow a similar technique and find out what will be the electric field, and also try obtain a graph of the magnitude of the electric field as a function of r. Now electric field due to a line charge distribution, a linear charge distribution. So what I consider here is a straight, okay, charge wire whose thickness is negligible. So wires whose thickness is negligible, they are termed as filamentary wires. So we have a filamentary wire which is charged, and it carries a uniform charge density. Okay, so charge density is lambda. So lambda is the charge per unit length. So we want to find out the electric field due to this linear charge at a distance r. Okay, let's say at a distance r. So what we do is, the Gaussian surface, the appropriate Gaussian surface here will be a cylinder. So we consider a cylinder whose radius is r and whose length is L. Okay, so this is our Gaussian surface. So the cylindrical symmetry guarantees a radial electric field. Okay, so because of the cylindrical symmetry, we know that there is going to be a radial electric field. Okay, so this implies, again, as we saw previously, the ends, they don't contribute to the total flux because the electric field is perpendicular to the area vector. So as a result, the total flux to the Gaussian surface, this is going to be equal to 2 pi r L E. Only this area of this curved surface that is going to matter. So that area is going to be circumference of the circle times the length. So 2 pi r L times E. E is constant everywhere on the surface. And the total charge which is going to be enclosed, that is really easy because we have a linear charge density. So I want to find out what is the total charge inside this. That will be simply equal to the linear charge density times the length, okay, which is enclosed inside this Gaussian surface, and the length is the same. That length will be the same as the length of the cylinder itself. So this is going to be simply lambda into L. So by Gauss law, we have the total flux, which is 2 pi r L E, that is equal to 1 by epsilon naught times the charge enclosed, which is lambda L. Okay, and this gives us the electric field to be equal to, so over here you can see this L will get cancelled, so that means the electric field is independent of the length of the Gaussian surface, which is what we expect, okay, because the Gaussian surface is just a imaginary construct that we make. It does not have any physical significance, so it should, any trace of the Gaussian surface, it should vanish. So by the cancellation of L, it means that the Gaussian surface does not play any part in the expression for the electric field. So electric field will be simply lambda by twice pi epsilon naught r. Okay. Now this is an infinitely long linear charge distribution, and if you remember one of those exercises that we had done where we found out the electric field due to an infinitely long linear charge distribution, okay, using the Coulomb's law, over there we had painstakingly found out an expression, and I had given you all I did it for a semi-infinite linear charge distribution, and I had asked you all to find out the electric field due to an infinitely long charge distribution. So over there, if you just apply the appropriate limits of integration, you will find that the electric field is going to be like this only, lambda by twice pi epsilon naught r. So I suggest that you go and check, but just imagine how much of effort we had to put to find out this result using Coulomb's law, and just see the number of steps, how elegantly we have been able to find out the same result in this case. Okay. Now finally coming to the electric field due to using planar symmetry. So I want to find out the electric field due to an infinite flat sheet of charge. Okay, so I have a sheet, okay, this is the sheet, it's a flat sheet, it is infinite in extent, and it has got a surface charge distribution of sigma. I want to find out what is the electric field, okay, at points on either side. So what we do is the field at either side is perpendicular to a plane because of the symmetry, and the field has got the same magnitude in the opposite direction at two equidistant points. So if I have one point here P, another point P prime, which is on the other side, such that this P is, if it has a distance r, on the other side P prime is at a distance, the same distance r. Okay, so the 2 points, okay, two equidistant points P and P prime, which are on either side. Okay, so this is guaranteed by the symmetry of the problem. The field is going to be same over this surface and is on the surface. By field I mean the magnitude of the field. The direction will be opposite, but the magnitude will be just the same. So what we do is we choose a Gaussian surface. This again is like our pillbox surface, except instead of a rectangular pillbox, we can choose a cylindrical pillbox. So the area of cross section is A. So this cross sectional area, that is A, and this surface is such that it includes this point P as well as P prime on its end faces. Then what is the total of flux through the Gaussian surface? This is going to be equal to twice AE, okay, because the side surfaces, they don't contribute. This area of cross section is A, so we have A, and this back surface also A, so total area is twice A, and the electric field is E, so twice A into E. So that is going to be the total flux through the Gaussian surface. And what is the charge enclosed by this Gaussian surface? That is really easy, because this is a surface charge distribution. All I need to do is I need to multiply the sigma with the area which is enclosed. The area enclosed is A, so A times sigma, that is going to give us the total charge which is enclosed. So sigma A is Q enclosed. So by Gauss law we have the flux must be equal to, okay, my mistake here, it must be, there should be a 1 by epsilon naught times, okay. The flux is twice AE. It is equal to 1 by epsilon naught times the charge enclosed, which is sigma into A. And then where this A gets cancelled, again the same thing as we saw in case of planar symmetry. Any trace of the Gaussian surface, it should vanish from the final expression for the electric field. okay, because the Gaussian surface is an imaginary construct. So the area, this area, cross sectional area, it cancels out, and that's what it implies. There is already, like I said, there is a 1 by epsilon naught, so this gives us E to be equal to sigma by twice epsilon naught, and r cap is the radial direction with respect to the planar sheet. So this gives us the electric field due to a infinite flat sheet of charge. And if you recall, we had done one more problem using the Coulomb's law, wherein I showed you the electric field due to a disk. So suppose I have a disk which has got a uniform charge distribution sigma. At a point on the axis of the disk, what was the electric field? We found out. And then I told you that if we integrated, because we were integrating from zero, we were using the angle that any one of these rings on the disk, concentric rings, like if I have a disk and I divide this disk into such onion rings, then the angle that is subtended by this ring, okay, by the width of this ring, okay, that becomes the integration variable. And this integration variable, we integrate this from 0, theta equal to 0 to theta equal to some value. So now if we are considering an infinitely large surface distribution, we just need to integrate from theta equal to 0 to theta equal to pi by 2. And you will see, if you go back to that problem and try it out, that same integration, if you change the limits from 0 to pi by 2, you will get this same result. Again, once again you realize how easily we were able to find out the electric field compared to finding it with the Coulomb's law. So that is basically the power of the Gauss law. Okay, so the Gauss law, it helps us to find out the electric field in a very, very elegant way in case of problems like this, okay, where there is some kind of a symmetry, namely spherical symmetry, cylindrical symmetry and planar symmetry. So with this, I come to the end of this lecture. Thank you.